Hi, my name is Skylar Johnson. I'm a senior supply chain management and business data analytics major at Western Kentucky University. This presentation will thoroughly address the challenges Staling Corporation faces with global shipping for its e-commerce orders through a 7-step business analytic model. Using RapidMiner software, the data was analyzed through multiple Receiver Operating Characteristic, or ROC, curves to identify the most efficient and accurate model to find a solution to the business model at hand. Based on this analysis, the development of an application is recommended to predict the most optimal transportation method tailored to the customer and the item being shipped. The 7-step business analytics process is: Step 1, business problem understanding. Step 2, data collection and understanding. Step 3, data preparation and feature selection. Step 4, model development. Step 5, model evaluation and interpretation. Step 6, final model and results communication. And finally, Step 7, model deployment. The Staling Corporation is an electronic goods and services supplier who faces logistical challenges in their daily shipments to their customers. Congestion and late deliveries are problems that Staling and lots of other merchants face too often. A 2019 case study analyzing various merchants and delivery methods revealed that over 6% of FedEx and UPS shipments, representing more than 508,000 packages in Q1, were delayed. Of these delayed, 72% exceeded 24 hours. Notably, these figures pertain to merchants with existing contracts with these shipping companies. For third-party logistics providers, or 3PLs, the late delivery rate worsens to 7.6%. A study by Late Shipment echoes these findings, highlighting that consumer electronics accounted for the 5.58% of late deliveries, trailing only sporting goods, 6.25%, and clothing apparel, 6.3%. Even corporations managing their own delivery services face similar issues. For example, Amazon's in-house ground transportation reported an 11.4% late shipment rate from Amazon Marketplace orders in January of 2020. By leveraging Staling Corporation's data to build a predictive model and incorporating it into a standalone application, the company can significantly reduce the risk of late deliveries. This approach enables Staling to select the most effective transportation method, air, sea, or ground, for each shipment, improving overall logistic efficiency. The Staling Corporation e-commerce data was collected with Kaggle, with a collection of 10,999 consumer purchases over several years. This data was categorized as secondary data, as it was not collected for the purpose of this analysis. It contains 12 attributes in a selected data formatted in a structured data format. The target variable, or what we are predicting, is whether delivery was on time or late. Before bringing the data into RapidMiner, it was received as a Microsoft Excel file with 10,999 rows and 12 columns of purchase data. For customer assurance, the data was pre-filtered in an Excel for easy access to data. The process included converting all columns to filterable, as well as converting the column reached on time from numerical to yes or no using a custom formula. With the filtered and collected data, the data file is much easier for the customer to preview and choose which variables to include in their analysis. Staling emphasized the on-time delivery of a product and if the product was marked as high importance. Now they can filter and focus in on the high importance items. Now that Staling has confidence in the data collected, the unfiltered data can be imported into RapidMiner. Verification that all data is transferred correctly, as well as checking for any missing data, is done at this stage. All variables were present in this case. Since the data is imported in its raw form, beside the reached on time attribute, conversion is necessary. The attribute ID is set as ID, and the reached on time is set as a variable to identify as the target variable. Variables gender, warehouse block, and mode of transportation, as well as product importance, were converted from nominal to numerical using comparison groups. As seen here, a correlation matrix was run, showing that the only variables close to multicollinearity was low and medium product importance. Stanley requested that all variables to be included in this model, so the attributes were left alone. To determine the best model to develop, a compare ROCs operator with logistic regression, decision tree, generalized linear modeling, deep learning, and neural net were run in RapidMiner. A sample logistic regression model was also included to provide customers with the probability values, while attributes with significant levels under 5% included discount offered, weight in grams, prior purchase, and customer care calls, high importance, and cost of the product. The client opted to retain all attributes further. This decision will prove to be valuable during the model evaluation phase of the development. After analyzing correlation matrices, comparing probability values to identify variables to eliminate, and evaluating ROC comparison models, we can determine the most suitable model for the customer. The ROC comparisons, reflecting both optimistic and neural biases, indicate that the decision tree model delivers the highest number of true positive predictions, which can be seen on the x-axis in these pictures here, while minimizing false positive predictions on the y-axis. Although the decision trees have minimal area under the curve, or AUC, it stands out as the most accurate option among the 5 models considered, making it the best choice despite its less than optimal look. In recognition of human error, the data was put through a predictive auto model in RapidMiner. Like the other ROC operators, the auto model was set to a neutral bias. Similar to the manual ROC comparison, the auto model found the best results in the decision tree. Next, a manual decision tree model is built with ID as the ID and reached on time as the label. Stanley requested to leave all attributes in, so they are converted from nominal to numerical using comparison groups and dummy coding. Splitting the data for testing and trading 70% and 30% makes this model a supervised learning model. The training data is then sent through the decision tree model, the testing data is sent through the decision tree model and the application model. Finally, a performance operator is added to rate the performance's accuracy. With all variables included, the first decision tree, seen on the left, is run. The first observation noticed is that offering a discount is nearly always associated with packages not arriving on time. However, this may be a case of correlation rather than causation. Discounts might be offering a response in late deliveries as the part of the company's offer to maintain customer satisfaction. Therefore, we chose to exclude this variable and rerun the model, as seen on the right. This highlights the fact that modifying a single variable can have influence on a performance model. By removing the discount offered attribute, the model also became more accurate. As found earlier, few attributes had a p-value lower than 5% for the test model. Less than 40% of packages were delivered on time, which is consistent with the research discussed in the business problem section of this presentation. The performance operator allows for the accuracy and classification of the decision tree to be assessed. The decision tree returned a 68.61 accuracy and a classification error of 31.39%. The matrix above shows that the model was able to accurately predict 960 deliveries that would not be on time, but missed 100 1,009 deliveries, making them false positives. The model predicted that 1,304 packages would be delivered on time, while only missing 27 false negatives. Removing the attribute discount offered improved the overall accuracy of this model by 2.09% and improved the class recall of the true yes by 23.21%. To affirm the client, different models were ran through the performance operator as well in the auto model, those being the naive Bayes, logistic regression, deep learning, and neural net. While the decision tree model proved to be the most accurate overall, there are only minor differences in the classification errors when comparing it to the deep learning and naive Bayes models. However, the decision tree model still has significant room for improvement. For instance, it can only predict on-time package arrivals with about 98% accuracy, but predicts late deliveries with not even 49% accuracy. Further adjustments to the model are possible. One potential improvement can be modifying the decision tree's criterion from gain accuracy to gain ratio to accuracy, which can be seen on the bottom of this slide. The accuracy of the model and the accuracy of delivering packages that are on time are decreased, but the accuracy of packages arriving not on time increases to 62%. As the model focuses on accuracy, the decision tree becomes more focused. The decision tree seen here is better suited for Staling's needs, as it is a comprehensive guide for understanding what affects late deliveries. The model shows which attributes contribute the most to whether a package will deliver on time or late. Beginning at the top of the decision tree, it can be determined that a package weighing less than 5,985 grams and costing less than $96.50 will be delivered late, which is in the blue, while a delivery weighing less than 5,985 grams and costing less than $96.50, it is more likely that that package will arrive on time, which is seen in the red. For a package costing less than $294.50 and weighing more than 1,003.5 grams, it is more likely for it to arrive late. A package that costs more than $294.50 weighs weighs less than or equal to 1,003.5 grams, and a customer rating of less than 4.5 will arrive on time. A package weighing less than 5,985 grams, costing more than $202, and was shipped by flight is significantly more likely to arrive late, whereas packages not shipped by air are prone to be delivered on time. While this model allows for moderately accurate predictions, it is important to note that there are several outside components that affect delayed shipping. Next is a visualization for the yes predictability of an on-time package using a gain and lift chart. As mentioned earlier, while this is not the most accurate model, the gain and lift chart provides an overall for the entire dataset and illustrates its alignment with our confidence levels for predicting future arrivals. For the 1,688 predictions classified as yes, 945 are accurate, yielding a confidence level of 58%. Overall, there is at least 58% confidence that within the first three bins, 945 packages will arrive on time. To better communicate with our client about future predictability, To better communicate with our client about how future predictability can influence their decision making regarding shipping, By evaluating various models, we identified the one that best suited our clients' needs. During this process, we eliminated unnecessary attributes, refined classification parameters, and transformed raw data into actionable visualizations to support business decision making. While this model ranked the highest in comparative evaluation, it exhibits certain limitations, including a low overall accuracy rate, high classification errors, and limited accuracy in predicting late deliveries. It's important to acknowledge that no model can accurately predict 100%. However, the client's primary goal was to have a predictive model of which can accurately forecast on-time package deliveries based on specific customer attributes. This is precisely what was delivered, achieving an almost 98% accuracy rate for on-time predictions. This model provides a robust foundation for initiating research and development planning for application software. As more customer data is collected over time, the model's accuracy and reliability is likely to improve, reducing classification errors. While not without its limitations, the model successfully meets the client's requirements for predicting on-time package arrivals. It's worth noting that several external factors such as natural disasters, equipment failures, or logistical disruptions can affect delivery outcomes and remain beyond the control of the shipping company or 3PLs. Despite the uncertainties, the model instills confidence in the feasibility of the development of a software application that leverages predictive analytics. This application can improve customer data, package weight, price. This application could incorporate customer data, package weight, price, warehouse distribution, and other relevant factors. For future enhancements, it is recommended to expand the data to include attributes such as economic inflation, customs regulations, distance traveled, and other logistical considerations. These additions could further enhance the model's precision and scalability, making it a more powerful tool for decision making.